You all set?
Yep.
All right. Okay, I guess yeah, everybody's in there. So so this is a speaking qualifier for RAM. We have so RAM is being co-advised by Howie and myself, and then we also have as committee Chris Atkinson here and Alex Pizza. Thank you both for coming. So RAM will talk for 30-35 minutes, hopefully, and then you know, any sort of questions throughout, that's fine, and then after that we'll have follow-on questions, and then the committee will discuss with regards to the fate of that particular qualifier. All right, with that, Ram, you take over.
Cool. Thank you, Max. Hi, everyone. Thanks for coming to my speaking qualifier today. I am Ramkumar Natarajan. Before starting, I'd like to thank my committee, Chris Atkinson and Alex Spitzer, and more than anyone, my advisors, Max Likachev and Javi Chasset. The title of my talk is Interleaving Graph Search and Trajectory Optimization for Aggressive Quadrotor Flight. And that means making a quadrotor, shown as a white robot here, to generate trajectories and negotiate narrow gaps and fly and make it fly from one side of the environment to another in this particular case. So I'll try to motivate this by taking a deeper look at an example of an aggressive trajectory. So here we use ellipsoid to approximate the shape of the quadrotor, and the trajectory is visualized using a series of ellipsoids. So a planner that can generate aggressive trajectories for a quadrotor should be able to reason over the topology of the trajectory. In other words, find the right combination of these narrow gaps to fly through the environment, and be able to do this global planning over large environments, and then be able to satisfy attitude constraints and generate dynamically feasible trajectories. At the same time, they should also be able to do this sufficiently high dimensional planning in the space of position, velocity, acceleration, and jerk, so on. And so in this talk, I'll present our planner, which has these properties and can generate trajectories for aggressive quadrotor flight. I will later get into these, show the same pictures and analyze the behavior of the planner. So here is the outline of my talk. I'll begin with the key idea behind our planner, then state the list of our contributions, then briefly go over the background material, and then describe the algorithm itself, and explain how this algorithm is adapted to the application of aggressive quadrotor flight, go over the results, and finally conclude with the future work. Okay, cool. So graph search and trajectory optimizations, they are two popular choices in motion planning with their respective advantages and disadvantages. Graph search, they are simple to use, usually have rigorous theoretical guarantees. They are global methods in the sense they converge to global optimal solutions, or provide globally bounded suboptimal solutions. But on the downside, they suffer from the exponential complexity, and hence they're mostly suitable for low dimensional planning. They also discretize the planning space, and hence can compromise the dynamic feasibility of the resulting plan. On the other hand, trajectory optimizations can be incredibly fast even in higher dimensional spaces, and can incorporate systems dynamical constraints. But the disadvantages are they have poor convergence guarantees, or sometimes no guarantees on convergence for the nonlinear case, and they're only local methods, and they only provide local conversions or local optimal solutions. So we develop a framework called INSAT for complex dynamical and articulated systems that brings the best of these two schemes, graph search and trajectory optimization, and I'm presenting that today. So let me summarize the contributions of our work. First, we provide a fast kinodynamic planner for aggressive quadrotor flight over large environments. Our planner is a meta framework that combines the best of graph search and trajectory optimization, and they can work with different choices of graph search and trajectory optimization. We also demonstrate that INSAT is algorithmically complete. where it is guaranteed to find a solution if one exists. And finally, we show that INSAT is superior than the other state-of-the-art baselines for aggressive quadrotor flight, both in terms of the performance of the planner, both in terms of the performance and the behavior of the planner. I'll briefly describe the prior work for planners for aggressive quadrotor flight. So I've divided the prior work into 3 different classes. The first one is the sequential method. Here there are 2 levels of planner. The first level either contains a search-based planner or a sampling-based planner that seeds the second level, which contains a trajectory optimizer. So Richter's work is one of the state-of-the-art and for aggressive quadrotor flight, where the first level is a sampling-based planner that is followed by a joint polynomial optimization to find a dynamically feasible aggressive path. The other work includes finding a set of convex, doing a convex decomposition of the free space. These methods decompose the free space into convex sets and run trajectory optimization within each of these convex sets and satisfy certain boundary conditions to transition from one convex set to another. And then there are works that use hand-picked gaps and gap detection algorithms to see the trajectory optimization. So the downside of these methods is that they either do not solve the entire planning problem in the case where you have to handpick the gaps or use gap detection algorithms, or they do not satisfy the attitude constraints, which is essential for aggressive quadrotor flight, especially in these 2 bodies of work. The second class of method are the lattice-based methods, where they build a lattice with pre-computed motion primitives, but due to dimensionality of the problem, these lattices can have huge branching factor and can even suffer from like deep local minimum or cursive dimensionality. And also the performance of these lattice methods significantly depends on the choice of discretization of both the state and the action space. So the final class, or the third class of methods, are the sampling-based methods, where we build a tree by sampling the free space. Kinodynamic RRT and LQR trees. Both of these methods have been demonstrated for aggressive quadrotor flight. However, as typical to all the sampling-based methods, although they can handle high-dimensional spaces, they have unreliable solution path quality and can take really long time to converge. They're also pretty sensitive to the sampling strategy, especially when the obstacles are close to each other in the case of narrow gaps, which is again essential for aggressive quadrotor flight. Okay, all right, so let us now get into the algorithm. I will first describe the overview of the algorithm, then show how the algorithm is adapted to the aggressive quadrotor flight problem, and then get back to the details of the algorithm again. Cool. So as you might have guessed, there are 2 components within our algorithm, the graph search component and the trajectory optimization component. Each of them are running in the respective stronger regime. The graph search component is running in the low dimensional space, and the trajectory optimization is running in the high dimensional or the full dimensional space. So the graph search is going to dictate what trajectory optimizations to run and with what seeds, and how to seed those trajectory optimization. And in return, the trajectory optimization will converge to a dynamically feasible trajectory, or say it cannot converge, with which we are going to accurately find the cost of the trajectory. And that is in turn going to drive the graph search in the correct direction. So these 2 components are interleaved until you find a feasible high dimensional trajectory from start to goal. So we split the planning space into 2 levels of dimensionality. So there is a low dimensional and a high dimensional subset. The low dimensional subset where the graph search runs typically contains the non-convex variables of the planning space, because the graph search can deal with it. And then there is the full dimensional or the high dimensional space, which consists of the derivatives of the spatial variables. So we will see how we are going to adapt this framework for the application in hand, like the aggressive quadrotor flight. So okay, so let us look at this case of a quadrotor has 6 degrees of freedom, 3 translational and 3 rotational degrees of freedom. The low dimensional subset for the planning, um, the low dimensional subset is going to contain the x, y, z, and the roll and pitch angle. We are going to drop the yaw because we assume the quadrotor is symmetrical about the yaw angle. The high dimensional variables consists of x, y, z, its first derivative velocity, acceleration, second derivative acceleration, and the third derivative jerk. So mathematically, for aggressive quadrotor flight, the goal of the planner is to find a trajectory by minimizing the jerk, the net jerk along the trajectory, and also the execution time. It should also, the trajectory that is coming out of the planner should respect the system's dynamics. It should satisfy the start and goal conditions and make sure that it is not in collision. And throughout the trajectory, the system should be within the limits of velocity, acceleration, and jerk, and also it should be within the control input limits. Right. So let us dive into the details of the algorithm. So what you see here in the right is the same, the schematic of the overview of the algorithm that I showed previously. So like I mentioned before, the low dimensional space is going to be discretized to build a graph. The low dimensional space consists of variables, the x, y, z, roll and pitch variables. So we run a typical standard graph search algorithm on this graph, which consists of a cost to come value for every node from the start, and there is a heuristic value, which is an estimate of the cost to reach from that node to the goal. So the cost to come is going to capture the cost from the start to arrive to that node. And then there is a heuristic value, which estimates the cost to go from that node to the goal. There is also a priority queue that dictates the order of expansion of these nodes in the graph. So let us consider an obstacle in the environment shown with this black cuboid. For the sake of understanding, I'm going to consider one intermediate step. So in this one intermediate step of the algorithm. So in this intermediate step, there already exists a few high-dimensional paths to reach to a few nodes in the graph. Let us suppose that we expand the node SL to generate a node NL. Here the subscripts L refer to the low dimensional space and the subscript H refers to high dimensional space. So now there are 3 steps for every newly generated node potentially. So we will first lift this newly generated node, the start node and the goal node to the high dimensional space, shown with this visualization here. And try to find a trajectory from the start to the goal via this newly generated node. If this, so we basically run the trajectory optimizer from the start to the goal via this newly generated node. If this trajectory is not in collision, then we add this high dimensional trajectory along with the node NL to the priority queue, with the priority as the cost of this high dimensional trajectory from the trajectory optimization. So the cost of the trajectory that is found by the trajectory optimization is going to drive the graph search, and we do that by adding by setting that cost that is coming from the trajectory optimization as the cost to come in the graph search that is running in the lower dimension. So, however, if this path that is coming out of the trajectory optimizer, if it is in collision or if it is infeasible, say it is like violating the control limits, then we enter into the repair phase. So the repair phase, we consider the high dimensional trajectory that already exists from the start to the expanded node. Here we show that in orange, basically the expanded node is SL. So we loop over the node starting from the earliest ancestor of this expanded node that is present on the high dimensional trajectory. So starting from the earliest ancestor in this path of SL to start, we loop over the ancestors only on the ones that lie on this orange trajectory or the high dimensional trajectory of SL. So the first such node is ML. So we consider the high dimensional trajectory to ML, which is basically this orange part. And we run an incremental optimization from MH to NH by satisfying the boundary conditions at MH and NH. So if this incremental optimization is in collision, is collision free, then we take the entire trajectory and warm start the optimization. So we run this warm started optimization from start to goal via NH until convergence, or if it starts to become infeasible. So we just warm started. Now and now we take the final trajectory, that is to reach NH from this warm started optimization, and add this final trajectory to the priority queue with the cost of the high dimensional trajectory. Okay, this is the visualization that shows basically the warm starting. Cool. So now that we know the algorithm in detail, let us see how we actually set up the trajectory optimization for this application. For that, I will consider one step in the trajectory optimization and try to explain this. So let us take three nodes in the low dimensional space. Each of them consist of the low dimensional variables x, y, z, roll, and pitch. So the high dimensional space consists of the same x, y, z, that is the replica of whatever is there in the low dimensional space, and the corresponding derivatives, the first, second, and third derivative. So we use this objective function to find a trajectory in between these nodes. That this was shown previously. However, we did not capture the roll and pitch variables in the high dimensional space. So if you see, look at this, the low dimensional node also imposes a constraint on the pitch and roll variables. But then these two variables are not captured in this high dimensional space. So let us see how we are actually handling this. So if you look at the Quadrotor's equation of motion, the first term here is constant given a quadrotor because it just contains the mass of the mass variable and the acceleration due to gravity and the negative ZW variable, which is always pointing downwards. We know that, but from the physics of the quadrotor, we know that the quadrotor can only apply thrust in the direction perpendicular to the plane of the quadrotor, which means it can instantaneously accelerate only in the direction that is shown by these orange arrows here. So using this intuition, we know that the attitude of the quadrotor puts a constraint on the instantaneous direction of acceleration. So we know the direction of acceleration given the attitude. All we have to do is basically figure out the magnitude of the acceleration. That we can do by eliminating this free variable FB, which is basically the thrust exerted. We can eliminate this free variable to generate the equality constraint, and we can move the variables around in this to back out the acceleration value given the attitude. So this is the relation that we have coming out of this equality. So with this relation, let's go back to the trajectory optimization setup. So earlier we were just capturing the x, y, and z dimensions in the high dimensional space. Although the low dimensional space was imposing a constraint on the roll and pitch variables, those were not captured in the high dimensional space. So with this newly developed relation, we can replace the free variables, specifically the x double dot variable, so that we can capture this constraint that is imposed by the variables roll and pitch from the low dimensional state into the high dimensional space, like we did here in each of these nodes. So, okay, so that is how we handle the trajectory optimization. That is how we capture all the constraints that is imposed by the low dimensional space when we go to the high dimensional space, and make sure those constraints are handled in the trajectory optimization during a call to an optimization. So, okay, so here is the final drill. We have the 5-dimensional low D space, which is running the graph search, and there is a 12-dimensional high D space running trajectory optimization. The graph search dictates what trajectory optimizations to run and with what seeds. And we use the relation that we derived in the previous slide to impose the constraints. And then that is imposed by the low dimensional nodes into the high dimensional space. And then in turn, the trajectory optimization finds dynamically feasible trajectories, and we use the cost of those trajectories to drive the graph search in the correct direction. So these two planners are interleaved until a high dimensional feasible trajectory from start to goal is found. Cool. So let us take a look at the completeness property of the algorithm and see how it works. The completeness property states that INSAT is guaranteed to find a solution if one exists. What that means is that if there is a high dimensional trajectory, tau h, in the high dimensional free space, xh free, then it is guaranteed that INSAT will find a high dimensional trajectory, tau h prime, in that high dimensional free space. So here is a brief sketch of the proof. I am not getting into the details, but using the property of the differential flat, using this property called differential flatness for a quadrotor, and the way we split the dimensions between the high dimensional space and the low dimensional space, it can be shown that if there is a high dimensional trajectory in the high dimensional free space, then there is a low dimensional trajectory in the continuous low dimensional free space. So this is the continuous low dimensional free space, and this is the corresponding low dimensional trajectory. Now, if we can assume that we can construct a graph by discretizing this low dimensional continuous free space in such a way that the graph has a path in it that corresponds to the trajectory in the low dimensional free space. So then this graph is sufficient for INSAT to search over and do the optimizations it does, and guarantee that it will find the high dimensional trajectory. So the way it works is that we use the property called differential flatness to basically, and the way we split the variables between the high dimensional space and the low dimensional space to ensure that there is always a corresponding trajectory in the low dimensional continuous space. If there is a solution to the problem, then we use we make an assumption based on the construction of the graph to discretize this low dimensional free space to basically ensure that there is a path in the graph if there is a trajectory in this low dimensional continuous space. Now INSAT can operate on this graph. It is sufficient for INSAT to operate on this graph to and basically make the calls to the optimizer the way it does to find the corresponding high dimensional trajectory. So the full, a more rigorous version of the proof is in the paper. Feel free to take a look at it. So here are the results. So these are a few trajectories that is generated by the INSAT planner. The goal in this environment is basically to find a path from the leftmost side, from basically between the extremes. Start from the leftmost side before all the walls, and basically reach the end on the other, reach the other end after all the walls. So we use again ellipsoid shape to approximate the shape of the quadrotor, and the trajectory is is represented using a series of ellipsoids. The color coding along the trajectory represents the magnitude of the velocity, instantaneous magnitude of the velocity, and the direction of the arrows along the trajectory indicates the direction of instantaneous acceleration and its magnitude. So there are some really interesting behavior that the planner generates. So the planner generates these helical paths for stability or to avoid vortex ring state, and basically not to reduce speed, in which case it can just, if it has to basically reduce the speed, then it could have slowly hovered down instead of generating this helical path. But because we are optimizing also for the time variable, these helical paths are more efficient so that the speed doesn't go down. We also see that this planner generates a swing maneuver to basically fly back and forth before it can reach the narrow gap, so that it can meet an attitude constraint that is imposed by that narrow gap. Some other behavior we see is that you can see that the planner basically reaches a very high velocity, like you can see from the shade, the color coding here, to enter this narrow gap, and then later again it breaks before it reaches the next wall, and then flies back and enters the next narrow gap. So this behavior is a direct consequence of interleaving graph search and trajectory optimization that cannot be obtained running either of them in standalone or in sequence. So here is the quantitative results. So this, I call this environment walls and windows because this is similar to a quadrotor flying through the windows of some tall-rise buildings. So in this, this column basically shows the number of windows per wall, and there is the number of walls in the first column. So I'm comparing this our planar INSAT with the lattice-based method as the baseline here. So we can see that INSAT basically consistently performs well in terms of the planning time compared to BASE, where it actually has lower planning time, I think, in almost every instance. This one case where it has comparable planning time, you can see that the baseline has a poor success rate. And we can also see that INSAT consistently has a very high success rate. This also reflects that the planner is complete. We terminate the planner after 300 seconds and basically calculate the success rate only the ones which found a plan within those 300 seconds. So here is the visualization of the plan from INSAT in a different environment. This is the standard below garage office. This is an indoor environment with a lot of cluttered spaces, and there are gaps that are smaller than the size of the quadrotor. So it has to again generate these non-zero roll angles to enter these gaps. We use the same visualization here. You can see that the planner once again generates a nice behavior to reach from the start to goal here. I'll show a video of this later in the coming slides. So this is the results for the indoor environment. So basically here we have the below garage environment and the MIT Strata Center. We compare INSAT with two different baselines in this case. So the first baseline is the same lattice-based method, and the second baseline this baseline is a sequential method that I described earlier. So this method consists of a sampling-based planner that seeds the path for the trajectory optimization. So we see that the sequential method obviously has very less planning time compared to INSAT. However, the success rate of the sequential method is very low, especially for really cluttered environments. This is because the sequential method heavily relies on the initial seed path that is applied by the first planning component, which is either the search-based planner or the sampling-based planner. So basically, it is a greedy method. If that seed fails, then it would never find a feasible trajectory. One more interesting comparison here is that we see that the baseline A and INSAT has equal success rate. However, and also the baseline A has less planning time compared to INSAT. But then this is because we ran this experiment on a 2.5D setup for below garage. That means we restricted the start and the goal to be on the same plane and made sure all the primitives that are generated are restricted to like a constant height throughout. So when that is the case, the lattice-based methods tend to perform better because the performance rapidly increases when in lower dimensions for lattice-based planning. However, if you go to more complicated environments like the ones in 3D, we can see that INSAT performs well. Once again, we see that INSAT has really good success rate. So here is the video of INSAT running in gazebo simulation. So there are three different environments here, the walls and windows environment. I'll first, what you see in the left is the visualization, and the right you have the simulation. So if you cannot see the quadrotor here, I mean, it's really small. You will be getting a close-up view in the later part of the video. Here is the close-up video. As you can see, there is an attitude constraint that is imposed by this narrow gap because the quadrotor is smaller than the gap, and it satisfies that attitude constraint. And when it comes out, again, the quadrotor swings back and forth to accumulate enough energy so that it can satisfy the next attitude constraint, that is, then again flies back and forth between the narrow walls in this helical pattern to basically rise up in altitude, and once again satisfy the attitude constraint to so here is the below garage office. So this is a slightly different path from what I showed in the slides earlier, I guess. I think it is running with a different suboptimality parameter for the low dimensional graph search. But once again, we can see that in close-up. So the quadrotor first generates this long suboptimal path to basically safely break, and then enters this tight gap. And then there are these two gaps to negotiate. So it quickly negotiates these two gaps and then finally reaches the goal. So the final environment is this mighty Stata Center. I just tested on this environment because it has more clutter than the Willow Garage, because that office environment looked slightly more structured. It's really hard to spot the quadrotor here. Sorry. Yeah, because of it's very small here. But okay, so I will conclude my talk by basically summarizing what we saw. So we introduced this meta framework called INSAT that can combine the benefits of graph search and trajectory optimization. And then we demonstrated how this framework can be adapted for this application of aggressive quadrotor flight. We also showed that INSAT is provably complete, and INSAT also actually generalizes to other applications like planning through contact. This is something that we have been working on recently. So the future work, there are some downsides to INSAT. Like INSAT, I mean, the speed of INSAT basically is heavily relies on the smart formulation of trajectory optimization, and also the speed of the trajectory optimization. In the future, we wish to substitute that with faster black box or learning-based methods, so it can increase the overall speed. And also, tracking these trajectories is a huge burden on the control side. I'm sure Alex Spitzer, I mean, he has an entire thesis on this. So, so basically we want to make INSAT a more incremental planner so that it can suit these real-time applications. With that, I will thank you once again for coming to the talk, and I'll take any questions.
Thank you very much, Ram. I think the typical process is that the qualifying committee goes first, and then the audience goes first. And I think if I remember correctly, typically it's the student on the committee goes first. So Alex, if you don't mind, maybe you can ask any sort of questions you have. You okay with that?
Sure. Yeah. Thanks, Ram. Really cool results. I'm wondering, so I have a few more detailed questions than some high-level questions. In your planning time results, there's a large variance in the planning times around slide 90, 96, 94, and I'm wondering what's changing between these trials? How many trials did you do? And I mean, it seems like the variance or standard deviation here is twice the actual mean. So is that just some starts have really long planning times, or why is there so much variability here?
Okay, so you're basically asking about this parameter here, right? This value.
Yeah.
Yeah. So I just ran it over 50 different start and goal locations. Obviously, the map is the same between the trials. It is just that if the start and the goal are really close to each other, sometimes. I mean, I had a threshold that it shouldn't be super close, but still, sometimes if it doesn't have to go across any of these narrow openings, or that is the place where the low dimensional search and the optimization spend a lot of time. Basically, the low dimensional search spends a lot of time. But if that is not there, then the planner exits really fast. And that is the reason for this variance.
I see. Okay. So you're saying if there was no obstacles and you gave it just a straight line start to goal, it would find the solution very quickly. Is that right?
No, I mean, basically what I meant was, so in this environment, if you had the start and the goal within this cubicle, I mean, I generated start and goal randomly, right? If it is within this cubicle, then it doesn't have to deal with any of these narrow openings. In that case, the low dimensional search just directly proceeds to the goal because, okay, I think I should say that the heuristic here is, I mean, it's just a backward A star computed, backward Dijkstra computed from the goal in 3D space. So the heuristic really guides it straight into the goal. And if that is the case, the INSAT exits really fast because we are not capturing the roll and pitch angles in the heuristic. It struggles in these narrow openings.
Yeah. Okay. So I was interested that you put the attitude constraints in the low-level search. So if you had a spherical quadrotor, would there be any need for attitude constraints? It seems like the only reason the attitude constraints are in the low-dimensional state is so that you can, change the attitude so that you can go through narrow gaps. Is that right?
That is correct. Yeah. So there is no requirement that it has to be in the low-dimensional space, but because we are dealing with, I mean, especially I wanted to show it going through these narrow gaps. That was the reason, primary reason. Because, like I mentioned in the previous work, there are so many papers, especially from the ETH group, which just tries to find this trajectory for one narrow gap. Like there is no global planning mechanism that works in these large environments. That is the reason I wanted to solve that problem, and because of that, I added that in the low dimensional.
And about the discretization of the low dimensional search space, did you find any issues where, if your discretization didn't line up with the environment, you wouldn't find the trajectory you wanted? Like, for example, let's say the gap is small enough so that it's only exactly one point that the quadrotor could pass through. And if your discretization misses that point, would there be a solution?
No, there wouldn't be. But then I think, so the way it is, at least if you just wanted to give me a theoretical answer, we assume that the low dimensional graph construction captures any path in this low dimensional space, and if this graph can capture, then INSAT will find a path. However, if you're saying that we miss that in the graph, then no. But so yeah, it is very sensitive to discretization. But then the way it is still better than purely discrete methods is that in lattice-based methods, you're discretizing all the 12 variables, whereas here you're only discretizing those 5 variables, so there is less hyperparameters to play with. Yeah.
Okay, and how might you use environment information into this method? So is there any way you could use some kind of topological description of the environment or some environment information to speed things up, or maybe be less reliant on discretization?
I don't understand. So how much of environment information? Can you repeat it?
So currently, as far as I can tell, you're not using the environment into kind of to bias your discretization or bias the samples that you're considering.
Right.
So
yeah.
how much you use if you had a map of the environment to kind of tell you where you should sample and give you better points to add to your graph search?
Right. So if I understand it correctly, if you're basically saying that we can do some kind of like a multi-resolution discretization in the environment that nicely captures free spaces and narrow gaps, then yeah, this algorithm should, I mean, it should work because the framework is meta framework, and if you replace the graph search component with a multi-resolution component, a multi-resolution graph search algorithm, I don't see a reason why it shouldn't work. But does that answer your question?
Yeah, I think that does. I'm just looking for some way that to maybe speed up the time. Where if you have lots of free space, it would take less time. But okay, great, thanks.
Yeah, but that was something. I mean, I always wanted to do it when I was running these experiments because it looked like, I mean, it was spending wasted search efforts in open free spaces, and then like I don't have to do that, right? Like it is super easy if I have a multi-resolution low dimensional search.
Okay, thank you.
Thanks, Alex. No other questions? Is that right, Alex?
No, yeah, for now I'll pass it off to the other members.
Okay, thank you. Yeah. Chris, do you have any questions? I'm sure you do.
Yeah, sure. Let me put some questions in the chat. and then you can sort of decide what you want to do about them. Let's see, let's hit that one. Okay, the first question is this problem really worth solving? It is, for complicated environments, your model is unlikely to be accurate enough to really do this kind of stuff without practice. I believe you could, with some kind of learning, execute one of these trajectories, but because of things like ground effect, which in this case is due to any nearby surface, I don't think your models are going to be that good. Also, my understanding with these drones is that their state estimation isn't that good either. And it takes a little time for their estimates of where they are to sort of converge. So given these limitations, the question arises, who cares whether you can optimize some super duper trajectory?
Okay, so I can probably answer this question in two ways, right? So number one, if all I'm worried about is just doing the planning and generating the trajectories and leave the job of tracking it to the controls people, then sure, someday controls will catch up. I don't know. Like, obviously, there are aerodynamic effects, like you said, the ground effect, which are hard to model, but I can evade by saying it's not my headache. But then the other aspect is where is it really worth solving? I mean, the framework is pretty generic, I guess. So there is some credit to that. And we showed that the framework was able to, at least from the planning point of view, was able to generate these cool trajectories for aggressive quadrotor flight. So what I'm trying to say here is that such a behavior, it is not possible if we are running either of these methods standalone or in sequence, right? So there is some novelty to it in terms of both behavior and performance. So that is the, but I'm sure. So the thing is, like, I showed it in these environments where I was just pushing it to generate this cool behavior. That doesn't have to be the case. I mean, we can use it to plan even in open environments where we don't have to deal with all this aerodynamic effects, right?
But then boring old trajectory optimization is going to do very well, and the graph search is not going to help much.
That is right. Yeah. So I mean, I think that's why I'm motivated with the application.
Yeah. Okay. Second question. Given that state estimation has a time constant, how would you take that into account in planning?
One second. So your question is like, how the state estimation is not perfect. How will I incorporate that in planning?
Yeah. So a Kalman filter in the end is a filter, and by choosing its parameters, you're effectively choosing the time constant of how long it takes state estimation errors to die out. And you know what those time constants are. You designed the filter. So how do you take into account the certainty that your state estimation is imperfect and it takes a while for errors to die out? And you have to hit a window with sort of particular accuracy, or you're going to have a high probability of hitting the side of the wall.
Right. At least in these experiments, so there were no noise or disturbance, right? But then that is something I mentioned in the future work too. So I mean, in one of the future work, I was saying that both the controllers find it hard to track these trajectories, and also the estimation is not great. But then one way to go about it is that you do this in a more receding horizon fashion, where you keep rerunning the planner. However, if your question is more about, so at the beginning, the estimation is very bad, and as the robot starts moving, the estimation tends to converge. What will you do at those beginning stages? Is that, if that is the question, again,
No.
this is,
Every time you do a high curvature maneuver, you're going to, due to modeling errors, create error. So you're going to have errors, even though there are no external perturbations. Your modeling error is going to give you perturbations all the time. And as you fly through one window in your setup, you're now facing a wall, and your knowledge of where you are is going to be off. And it's going to take a certain amount of time for that error to die out.
Yeah, the focus here is just a planner, and
right. But I guess the higher level point I'm making is you got to plan to sense as well as plan to act, because your sensing limits what you can do in terms of action.
So then the answer is that, I mean, by doing it in a more receding horizon fashion, you can solve part of the problem, right?
No, I would argue that the right way to do it is to plan in terms of a belief state, rather than you have to represent uncertainty explicitly if you're going to take it into account in planning.
Right. Okay. So
I don't know how to solve the problem. That's just my suggestion. Okay, let's move on to the next question. So when we did this hierarchical stuff on legged robots, we found we had a problem that at the low level, a particular plan was infeasible. But there was no way to tell the high level why it was infeasible, because the high level didn't have any representation that was capable of representing that. So we essentially had to poison parts of the graph or parts of the high level plan in a very crude way to prevent it from continuing to ask for infeasible, essentially low level trajectories. Have you run into that problem, and what do you do about it?
Yeah, so I see this problem when I'm asking the high dimensional planner to generate trajectories that vary significantly in the rotational angles between two low dimensional nodes. For example, there are two low dimensional nodes which vary more than like normal. I mean, it's obviously discrete, but then more than normal between those two nodes in the rotational degrees of freedom. In those cases, the high dimensional trajectory, it might still converge to a trajectory, but then the cost is just super high that it is not. It is. I mean, it looks really weird. The optimization converges, but then it is not at all trackable. So in that case, because I'm using the cost that is coming out of the trajectory optimization inside the graph search, the graph search took care of it. Like basically those trajectories had super high cost, and then they got put into bottom of the priority queue, and then they never got expanded. So that is how it got handled automatically.
Right, and assuming your graph essentially boils down to which windows you choose at each step, and you either can completely not do a window, or you can or basically every time you go through a window, it's a good thing, then that approach works. But suppose you have a window where, half the time, depending on how you come through previous windows, it's really good, and half the time it's really bad. Your graph search doesn't have a way of representing that.
Sure, but then in the limit, we anyway explore the entire space, right? Because we are in the low dimensional space, we are running an exhaustive search. So So the graph will capture, I mean, it will eventually try out all these windows. Say, for example, you're coming, if we take this, yeah, you're coming in through this window. Maybe it is super hard to enter the window right in front of it, but it was easier to fly this way and enter this window. However, if this window was, I mean, there is a window here. However, if this window was not, if it is not possible to enter through this window, and this was the only possibility, we do search the space exhaustively. So it would have flown back here, and then maybe it did some swing maneuver like it did here to again enter this window itself. So the exhaustive search, again, we are relying on that exhaustive search property of the graph search to figure that out.
If you're NASA and you're planning planetary missions and figuring out what planet do I slingshot around in order to get to Pluto, I agree, you can afford to do exhaustive search. But if you're a flying vehicle flying through trees or buildings, it is unlikely you're going to have the time or computational resources to exhaustively plan. And chances are you're going to do pretty superficial trajectory optimization. I would argue you should only do like 3 rounds of gradient descent. And if it doesn't turn into something really good, you should move on to something else.
Yeah, I mean, so there is a exit button even within the trajectory optimization, right? So I don't keep running it forever. So especially in this planner, because we make so many repeated calls to the optimizer, I don't even wait as much as I would wait if I'm just calling them standalone. The threshold for exiting is pretty high, and I just exit quickly. But on the other hand, once again, so far the framework is just it's an offline one-shot framework. Yeah, there is this obvious downside. It is not working in a receding horizon. No incremental planning. Maybe if there is incremental planning, it will keep until there is until the exhaustive search converges to entering one of these windows. It will keep spending time in between these walls. And the final answer, again, the philosophical answer is this has always been the conventional wisdom that exhaustive search takes time, right? But Max's lab definitely has progressed so much in that direction.
Okay, let me go to the last question. So in one of the early related work slides, you basically said, planning with primitives doesn't work. On the other hand, from Max's lab, there's been all kinds of work on how experience helps you plan. And as I understand it, what they essentially do is they use past experience to generate new primitives, and thus you have to plan in terms of primitives to make use of experience. So how do you make use of prior experience to do this stuff? Is it conceivable, for example, that you would have an agent learn a go through window skill, and you would compose a sequence of go through this window, that window, next window, a series of end skills?
Yeah, I think I answered that question slightly differently when I was saying we can maybe substitute these trajectory optimization methods with black box methods so that they have skills, and then we are just searching over the skill. In other words, the high dimensional planner could just be throwing out skills, like you were saying, and all we are doing is just, yeah.
But then you're not doing trajectory optimization at the low level.
Yeah, I'm not doing trajectory optimization at the low level. I think this method regresses to several other methods where we are just searching over skills. But yeah, we're not doing trajectory optimization at the lower level. We just have these skills. Oh, I see. Okay, so you're saying that. Okay, so the reference that you are making is if there are experiences in the lower level, how will I use that?
I've flown through a lot of windows. I want to aggregate all that training data and turn it into a skill.
I think I mean, if there is something that is coming out of an experience, maybe we handle that by giving them lower cost to come in the graph search, so that they get prioritized more than the newly generated nodes. So that way you prioritize experience over exploitation.
The reason I asked this question is I'm sitting down here in Florida watching pelicans fly, and they are so amazing. They use ground effect on waves. So they're gliding a foot above the side of a wave, and they follow the wave, and then they hop over it and follow the next wave. They're doing incredible things. And, you know, I can't believe they're basically computing, you know, fluid models of airflow. That's got to be a skill.
Yeah, right. Agreed. I think when you mentioned that, so again, there are these questions that you're asking from sensing, modeling, and estimation side, right? The framework is agnostic to any of those. I mean, if you can model, or if you can even have those skills, the framework still works. And yeah, those are some amazing behaviors that birds do. Like, I mean, they have agreed.
All right. Thank you very much.
Thank you.
Thank you, Chris, for a wonderful set of questions. I was afraid you're not going to have any questions. Let's see. Howie, do you have questions for Ram?
Yeah. So Ram, just so you know, I'm trying to take notes on the questions and your presentation, so I didn't want you to think I was typing to my girlfriend or something like that, and I don't have a girlfriend. So my wife doesn't let me date. This was a nice talk, and your communication is getting better and better. I had two questions, and I worry that my two questions are a variation of what Chris was asking. So I don't want to waste time. So let me ask the easier one first. So it sounded like Chris's first question was, hey, what's this good for? And, you know, your work, the combination low dimensional search, low dimensional space to seed a high dimensional search. And then his third question talked about, if you're flying through really fast through a wooded forest, and I guess the supposition there is that you don't know where the trees are in front of you, you really can't plan that far into the future anyway. So we may as well just use, in his words, boring old trajectory optimization. So it made me think, what is your stuff good for? I want to ask the question again. Is there a problem? Did Chris pick a problem that wasn't important for you, and there's other important problems? But why is this good?
So, I mean, for one, okay, I can, to answer the second question, or Chris's third question first, there are methods that make progress in that direction, right? Like there was this paper, or like this work called Push Broom Stereo from MIT, which is basically was dealing with birds, I mean, or like fixed wing aircraft flying through these forests, and figuring out these narrow gaps between the trees online. So the framework is agnostic. So I mean, when I say what is this work good for, it's just the framework and the way we use the way we call the trajectory optimization within the graph search, and how we.
However, Ram, I'm sorry to interrupt you. We would like to believe that everything that you're working on for your thesis and for research is good for something. Okay. In other words, I hear you saying, well, really, there's no good or bad. It's a framework. But certainly it has, if you're presenting an example of a quadrotor flying through tight spaces, you have to say why your method is good.
So, I mean, for one, the baselines that we were comparing with, or any of the other baselines that I knew, it wasn't even able to solve the problem, like for this environment.
So I'll put the burden of the entire community on your shoulders. Why is all of that work good? In other words, why is doing any kind of trajectory optimization based approach for robots that have high dimensional, say, configuration or state spaces flying through tight spaces, whether it's your approach or anyone else's approach? Why is it good? If there's all this uncertainty, or if you're always gonna have to plan just 2 or 3 steps into the future anyway.
So in situation, I mean, again, if we are just worried about like real world application, then I think the controls have to catch up. But for indoor applications,
shouldn't we worry about real world applications? You know, we are roboticists.
Right. Yeah. But then there are a bunch of applications that is like indoor surveying, where you can estimate the state with really high certainty. Like, for example, there was one project where we were flying quadrotors inside a museum. So in those cases, when you can estimate, these methods can be useful, right? Because for those real world applications.
Maybe I'll stop this line of reasoning, because I'm worried I might be driving you in circles, and for that I apologize. Let me go to the second question. So I always worried with this work that somehow when we were seeding a path in the low dimensional space, it would not necessarily lead to an optimal path in the high dimensional space. So just to use an example, you know, in the early days, we talked about the homotopy classes. Now, again, in these 3-dimensional space, well, I guess with the window worlds, there's homotopy classes that are significant. So the question is if you find a path in a homotopy class in a low dimensional space, does that homotopy class necessarily correspond to an equivalence class in a high dimensional space through which your candidate path from the low dimensional space is a good seed for a search in the high dimensional space? So that was my worry, that this mapping didn't occur. But let me say it, the worry in a different way. Just using the plane for example, just to make it easier, you know, you have just imagine an object in the plane. It could be a square, and you're a robot. And when you get to the square, you have a choice of either going to the left or going to the right. And obviously, going to the left is one kind of sort of suggests one homotopy class, and going to the right suggests another homotopy class. Now, of course, looping around the objects are also homotopy classes, but let's forget about that for a second. So my question is, I was worried that a path in the low dimensional space that goes to the left could maybe have its optimal version of that become a path that makes you go to the right. In other words, why are we so sure that once we have a path in the workspace, that the trajectory that we eventually optimize in the high dimensional space leads to a path that's in the similar equivalence class? I'm trying to avoid to use the word homotopy class in higher dimensions, but the point is, how do we know what starts going to the left leads us to an optimum path that goes to the right? Because I feel like that's an assumption you're making. And then if that's true, if that's the assumption you're making, I worry about the completeness of your work.
No, right? Because let me use the word equivalence class. So whatever path that you seed from the low dimensional graph search to the trajectory optimizer, it does not have to converge to the same equivalence class, even after you project the trajectory back into the low dimensional space. So basically what I'm trying to say is, you start with some homotopy class, go to the high dimensional space. After it converges to some final trajectory, if you project that back to the low dimensional space, it does not have to be in the same homotopy, because the high dimensional trajectory optimization is unconstrained in between the waypoints. We just restrict, I mean, even those waypoints are added incrementally. So it does not have to be in the same homotopy class. And that basically gives us 2 benefits. Number one, we are not sticking to one homotopy class. And number 2, because the high dimensional trajectory optimization is unconstrained, it is also faster.
Okay, so I was expecting, thank you. I was expecting you to say that because you're doing a graph search in the low dimensional space, you're somehow enumerating a bunch of candidate paths. So, okay, it's a different question. Okay, I'm okay with that. I'll be quiet. I thank you for the question, for the answers. Thank you.
Thank you.
Hi, thanks, Kawai. So I guess I will just have a few quick things, and I want to make sure that the audience get a chance to ask questions. The two things I want to talk is actually related to what was said earlier. So specifically with regards to the proofs that you have, isn't it more, so your first step in the proofs was that if you have a high dimensional trajectory, then you're guaranteed to have a low dimensional trajectory. And that's, basically due to the flatness, differential flatness of quadrotor. But it's more than that. Isn't it the case also that you are relying on the fact that given a low dimensional trajectory, you are able to reconstruct the high dimensional trajectory that essentially follows that?
Sure, but then I mean, basically, we go from the low dimensional trajectory. We impose the constraints back in the high dimensional space, at least whatever that is imposed by the low dimensional space, using the differential flatness as well, right? Because this relation itself, this basically comes out of that. I mean, so what differential flatness essentially says is that you can go back from the output of the system to the input using the derivatives inputs. Yeah.
Right. And so I think that is inherently being utilized quite a bit in being able to prove the completeness. All right. Because if you were not able to do that, then I think you would be relying on a trajectory optimizer being able to solve, first of all, a completely arbitrary problem and not trying to go through those waypoints. And you are restricting it to go through the set of waypoints in a low dimensional space. So, and that only works because you have that property of being able to go back due to the differential flatness. I think that relates to Javi's question as well.
You mean the homotopy question?
Well, yeah, the fact that if your low dimensional graph is exploring that particular path, it's you are, the way you're devising the algorithm is such that it's in a high dimensional space. It's trying to run the trajectory optimization, hitting through those at least some of those waypoints. And if none of them are feasible, you would not be pursuing the trajectory anymore further.
Sure. Okay, that is a separate answer. But then you were saying that this implication is.
So yeah, I guess yeah.
There's a double arrow.
Yeah, exactly. I mean, I understand for the visually you only had the arrow down because this is how the proofs goes. But I think verbally you're also saying that the fact that there is a high dimensional implies that there is a low dimensional. But that's not enough for the proofs. It's you're actually also relying on the fact that there is a structure to this problem in such a way that when you go from the low dimensional to the high dimensional, it doesn't go arbitrarily far enough low dimensional, right?
Yeah, yeah.
Yeah. So I think which somewhat affects your also arguments about a full agnostic property of the algorithm. It's not a fully agnostic. It's actually for a certain class of problems where you have that characteristic. Is that correct? Or at least some other class of problems where you can find the same type of relationship.
Yeah. So I mean, so the differential flatness is not just a property of the quadrotor. It is a more general property, and also it depends on the choice of variables that we consider as the input to the system. So yeah, it is our choice. Like for example, quadrotor is differentially flat for if we have the if we choose x, y, z, and yaw angle as the input variables. It is not differentially flat for some other set of variables, even with which you can control the system. Yeah, right.
Right. So there is a class of problems in general, and might be potentially more than just the ones that have a differential flatness, but there is a class of problems that your algorithm is applicable, and there's a class where it's not applicable.
Mm.
Okay. All right. The other question I had was with regards to the uncertainty that Chris mentioned. So there is a work where you can do the graph searches where the state contains some sort of a representation of the belief, and there's stuff from Nick Roy's, there's stuff from Tony Stantz's group on this and so on, where you basically represent uncertainty with some sort of additional parameters, like a variance, covariance metrics or whatever. And then you're making assumptions on how it's going to increase over time, either over distance or as a function of what type of actions you take and so on and so on. And you can do planning over it, right? So which I thought was actually a great, interesting possibility for you to consider. Is it feasible to do it? Like, would it be feasible to do it in your context?
So basically, you're saying those methods has that confidence measure within those when they make those state expansions, right? So the variance is captured, or like the uncertainty is captured in the graph search. Is it possible? I mean, then I have to figure out a way in the high dimensional within the optimization, within the trajectory optimization in the high dimensional space, to propagate that variance, which is for this domain, I think it is possible because there is an embedding between these two spaces, at least in certain variables. I mean, there is no embedding in the velocity and the jerk variable, but in general, we have to find a way to propagate that to the high dimensional. It is not natively applicable. No.
Well, no, I understand natively not applicable, but I guess it's something that potentially might be interesting to look at. All right, I'm going to stop here just to see if there are any quick questions from the audience. Are there questions from the audience? I guess there's a question from David.
Great talk. You mentioned, so we were just talking about the proof of completeness of your algorithm. I was wondering about optimality results. Do you inherit optimality or bounded suboptimality directly from the graph search, or are there other things that could go wrong here?
Yep. No, these methods are not optimal because no, I don't inherit either. The reason is when I make this expansion, it's very simple to explain actually. So when I make this expansion of this state SL to generate this node, and I traverse through the ancestors of the state SL to find the best parent, I arbitrarily assign a parent that is from one of these ancestors, and they could get rewired down the line later again. So because I arbitrarily change the parent and I don't propagate the values down the tree because of this change, I lose optimality.
Okay, thanks.
Any other questions from the audience? I guess we'll do the countdown. I guess, are there any other questions from the committee before the committee just kind of discusses the case? Nope. All right. Well, if there are no more questions, then the process is that we're going to stop here. The committee will basically have a discussion, closed discussion, and that means that everybody has to drop out, including you, Ram. But I guess you, Ram, the host, can you make me a host?
Yeah, okay. I will make you a host.
Right. And then why don't you drop off after you make me a host, and then I can text you. I think I have your text, right, to connect back. Is that okay?
Okay, cool. Yeah, cool. Thank you.
Ram, do you mind? Can you send me a text over phone number as soon as you disconnect so that I have your number?
Okay, yeah, I'll do that. All right, thank you.
Yep, thank you.
Hey, Max, could you also stop the recording if you don't want this to be recorded? I know that sometimes people forget.
Yep, thank you.